recapping what we learned from last time. The first thing was I demonstrated the applicability of the Hayden-Preskel protocol for quantum systems in thermal equilibrium. We found that information thrown into the quantum system ultimately escapes into or is ejected into the bath, the thing that keeps feeding the qubits into that quantum system. Second, we found or showed that it can be implemented with quantum circuits with logarithmic depth in the number of qubits by using so-called quantum circuits which are called two designs. These are relatively simple circuits composed of simple gates. And the motivation of restricting to these kinds of circuits is that is to make contact with sort of dynamics of local Hamiltonians. For example, take the SYK model. You have n fermions, but you have 4 interactions at a time. So that was sort of the motivation. And now the question is, do we see something like this in our setup? I didn't get a chance to talk about this last time. And the answer is yes. So let's consider our setup at late time, so after the page time. If you recall, the RT surface for the left-right system, or the quantum extremal surface, because the disconnected surface. This means that a message sent in from this time escapes the entanglement wedge of the left-right system. Right? The entanglement wedge is all of this, in a sense. So, and the time difference between this time and this time is precisely the scrambling time, beta over 2 pi times log of, interestingly, the thermal entropy above extremality. So S black hole minus S naught, the ground state entropy. The relevance of this scrambling time to near extremal black holes, which was actually studied by Stefan Leichenauer in the context of writing, computing out-of-time ordered correlation functions in terms of the shock waves in the eternal black hole geometry, and he finds the same scrambling time. That it's controlled by the difference between the thermal entropy and the ground state entropy.
So, I mean, this difference goes like t squared.
Correct.
So there's an extra log t. I mean, it's the scrambling time goes like 1 over t with a log t.
Exactly. But there's also G Newton in there.
I see. But the redshift, of course, just goes like t. I mean, the standard boost factor. So the chaos exponent is an extra log near extremality, or how does the extra log come?
Isn't it n times t inside?
Yeah, I was about to say that. There's a G Newton in there as well. So it's T over G Newton, T squared over G Newton.
Yes, it's t squared over g Newton. No, so SDH is like n times some power, right?
Yes, it's t squared times if you want n.
Yeah. Okay, so now log of that is log of n times log of t squared, plus log of t squared. And it's log of n then.
Yeah, so yeah, exactly. So you can ignore everything else.
Oh, I wasn't sure. Very close to extremality, so you don't go that close so that the t wins over the
get
other,
that.
because then
Yeah, of course.
approximation breaks down.
Of course, exactly.
Oh, okay. Then it's the usual.
Then it's the usual thing. Yeah.
But I mean, then did he actually, when you say he got this answer, did he get the log t part? Because otherwise you might just as well have said that he got, you know.
I suspect he did. I suspect he did, yeah. But
I thought he was saying that. Okay.
Yeah.
Thank you.
So what do you equate delta t to, what do you call it, scrambling time?
Let's consider the RT surface at this time, okay? So it's going to look something like this. I'm assuming even this time is past the page time. So you're going to have something like this. So the message is clearly on this slice, and therefore it is part of the R system, okay? But now the question is, how much do I need to evolve for the message to escape this region? And you just need to evolve by a scrambling time, and the message completely escapes your system. That's the observation here. Okay? Next, I wanted to go. Yeah, please.
This is that Rayleigh pulse
Oh,
of light going in is your n qubits going in.
Precisely.
Yesterday, and then the insides are the system, but it escapes that system because it's in effect in the bath, although
Yeah, 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 yeah.
space-time, it's inside.
Exactly, exactly, exactly.
And sorry, these factors of n come in because the how near the dot is to the horizon has some n in it.
That's right.
Has G newtons in it.
Yeah.
That's
If
right.
it was purely classical problem, there would be no n.
And
Yeah.
it's got a G Newton in it because you're extremizing the generalized entropy.
Yeah. One factor has a G Newton, the other one is not.
Exactly, exactly. Okay, next let me go over some examples. Oh yeah, yeah.
N is C.
Yeah. Basically,
No, 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 no. There's n, which is 1 over g Newton, and then there's c, the central charge of the matter theory.
Okay, so we come back to this thing that we are keeping C times G and fixed. Okay.
Well, actually, I mean, that point, I mean, let me see. So the only reason why we're working with large C is because we don't want to consider the contribution from the Schwarzian. Is that right?
The quantum.
The quantum graviton. But in principle, one can keep it and work with small c. And I don't think much of the story will change.
Okay, but then you have to sum all orders in G and, you know,
No, no,
do the full quantum problem.
no. We still have an h bar expansion, and we're just working to first subleading order in h bar.
You still have, but if the order H bar contribute, let's say we call the first contribution order 1, the classical one. If the order H bar plays an important role compared to it in where the extremal surface is located, then you'll have to keep all orders in H bar.
In principle, one would need to check that. I agree.
Right. So therefore, I mean, it's a non-trivial calculation.
Although, okay, I will only spend 5 minutes on this. If we go too long, then I'll stop. I'll just jump to the other thing. So let me just make the following, let me motivate why the other high order terms will not be important. So we have S is phi over G Newton plus S bulk plus possible higher order terms, which I'm going to write as G Newton times dot S. Okay? Now, let's ignore that term for a second. In this actual problem, when we extremize, so we take the derivative of S, we have d phi over G Newton plus the S bulk plus G Newton derivative of delta S. The thing that we find that happens, so these guys become comparable. But how do they become comparable? It's that this derivative becomes small. So this guy is of order G Newton, and so this term is now order 1. And this term is order 1. And so then they compete. It's not that this term becomes it's not that these two terms become very small or anything. So the only way that this thing can now become relevant is if this term goes as 1 over G Newton, which kind of seems implausible to happen. But ultimately, one needs to do the calculation. Just wanted to make that comment.
Can I just say the first, in the way you're doing,
Yeah.
if the gravity part to begin with is 1 over G Newton, then I would say that the first correction is order G Newton compared to the leading term.
Sure.
So it's
Yeah, okay.
order 1 in your way of computing.
Yeah, yeah.
This still means, I mean, your point is well taken. This still means that if that part is still giving a derivative contribution order G Newton, it'll be suppressed. So if this does work out, I think then your intuition will be
Okay.
good.
Okay,
But
okay.
I'm just saying, you know, it's worth.
Point taken, point taken. But yeah, yeah. Okay. Okay. Next.
So this is the part that much amount of time it takes the information to fall in.
How
But then black hole has to scramble it, right? It has to take some time to scramble it, right?
That's this point. That after, well, I mean that's this amount of time. So yeah, this time scale is that once the black hole is done scrambling it, it's already ejected into the radiation. Okay. Now let's talk about some examples of the entropy formula that gives very interesting observations. So this is the formula. We have to extremize over these islands. So let's first apply it. So this is this case. Okay. So this is just the entropy of R. Oh no, sorry. This case was the entropy of the union of the left and the right. It just so happens that at late times you get the same surface had you extremized just on a single side. But this is true for all time, okay? So the entropy of R, you have the extremal surface somewhere there outside of the black hole horizon. And again, you have this scrambling time business that I discussed there. If you compute the entropy of BR, which is the right bath, then this actually depends on details of the bulk theory that you're considering. I'll discuss this later in more detail. But in the case where you take the matter theory to be a large N CFT, then you find that there's no island contribution. You just have, it's just a usual von Neumann entropy of this subregion.
By that you mean you would, naively speaking, just use that log formula?
Exactly, just that log formula. In fact, the entropy is infinite.
Sorry, and that calculation is just like in your first lecture?
Yes,
Okay, very good.
exactly.
Okay.
And
the difference is that it's now one. In your first lecture, you had more.
exactly. So this is one, and this is infinite. There's an IR divergence, so you need to regulate it and so on.
Yeah. So in your first lecture, you got away by then calculating what was in the middle.
Yeah, yeah,
Using the same answer.
exactly. But if you compute the entropy of RBR, so the entropy of this entire region, including this point, then you find that the quantum extremal surface is the bifurcate horizon. Okay? So the entropy of R or R is dual to this region, let's say. The bath is not dual to any part of the bulk, but the union of R and the bath is dual to the entire right side.
But how do you do that calculation, just to understand? That is, so now, I mean, how do you include, when you say you include that point, what you're saying is, in effect, you're including, if you were to do it in an RT sense, that point is really the boundary of the entire block.
Yes.
And so,
It's where the boundary particle is, let's say.
so you're going to do the third one by embedding in one?
Yeah, it's gonna be clearer there. But the thing that you do is you just literally just apply this formula.
Yeah. An extra sense.
Exactly. So you apply that formula. So the von Neumann entropy of B union I is just the entropy of this entire thing. So first, let's move this point somewhere, not on the bifurcation surface. Let's say we're looking for the quantum extremal surface. This von Neumann entropy of B union I is the entropy of this half space interval. And the dilaton contribution is just a dilaton at the end of that point. And you extremise and you land on the bifurcation
And the
surface.
main difference between 1 and 3 is that the point on this dotted line is not frozen to be at a particular time.
Exactly.
So had you taken that in 1, had you taken that point on the dotted line? No.
No, but I mean, you can keep it on. You can keep it on that point. I mean, it doesn't.
So then I can't understand why the union of those two is not also an extreme.
So the union of these two. What do you mean?
Sorry, 1 and 2. Yeah, 1 and 2.
The union. This. So this is. Sorry.
The end point of 3 is different from the end point of 1.
Yeah, correct.
That's what I want to understand how that works.
Let me see. So let me give you the boring answer. I mean, it comes from just applying that formula.
Yes.
Um,
But you applied that. Yeah.
Let me just try to see that. Should us the log, the field theory contribution will be different in the two cases.
Yeah.
Because the slice extends all the way to space like infinity.
Right.
And so you
Versus-
add that field theory contribution with the value of the dilaton and extremis.
Yeah, but I'm not exactly seeing how the field theory contribution cares about where you went here.
yeah. No. It's. Sorry.
But it cares that in one case it extends all the way to the right end.
Yeah.
Sorry.
That's the difference.
So why the field theory calculation cares about where this point is?
Yeah.
Remember that the metric here is not flat. It's an ADS2 metric. And so there's a cutoff factor that really cares about where you are here.
Okay, I suppose.
In the first calculation also there's a field theory
Is that?
for that segment.
Yeah.
Which cares where that segment ends.
Yes. Yes.
And the third one also there is, right?
Yes.
Your question is why is the endpoint changing? Because the right end,
Yes.
in the ones on the one hand, in the first figure is ending at the boundary of the ADS2 region, and in the third figure is going all the way up to space like infinity.
Right. It just wasn't so clear to me that I'm just being. I see your point. It wasn't clear to me that would do it, but yeah.
Okay.
I didn't quite understand. So you take the union of this first figure with the second figure.
Okay.
Yeah. So that by
second
no,
figure,
no,
you're
no.
not really extremizing anything. Is that right?
Yeah, exactly.
That's somehow.
Oh.
Nothing is being extremized here, at least in this picture.
Because that's purely a field theory calculation.
Precisely.
And now you're doing Ryu-Takayanagi for the whole thing. That's another difference.
Yes. But there's something interesting here, that this region near the horizon is not dual to the right boundary, nor is it dual to the bath, but the union of the two captures the physics near the horizon.
So, in the third diagram, where is the thing anchored at the bottom?
Here, where is it anchored?
Just extend, it's a dot and a line, right?
That's right.
So the dot, the representation of dot is just a line in the bulk. I mean, that's your graphic formula. But really what you're doing is computing entropy of the dot, which is just sitting at the boundary.
Union the line.
Union the line.
Half
The
line.
line can be just chosen arbitrarily, and you're just choosing it to extend it from that point to
Infinity. It doesn't matter how I wiggle it here.
And it also doesn't matter where it's the dotted line because you can boost.
Because of the boost invariance, exactly.
In the last lecture, you said after at least some time, the artist of this, sorry, not the artist of this,
No, nothing happens here as a function of time. So as Shiraz just mentioned, this thing is boost invariant, so it doesn't care about which time slice you pick. However, here, this is what we did last time. We were computing the entropy of the left and right boundaries at some given time. Then you lose boost invariance, and that's why things can happen. But go on.
the island comes about.
In this case. But
Sorry, I mean, so the point is that although it seems like, you can continuously go from 2 to 3 by taking the point to the boundary.
Yeah.
Because there's a discontinuous change when you include it, because then the Ryu-Takayanagi
Yeah.
formula comes into play.
That's right. Yeah, but there's also this annoying thing about computing entropy in field theory. Take an interval and make the interval as large as you can. Take it to infinity. The answer is going to diverge. But the entropy of the entire field theory, including the infinities, is 0. So,
Is 0. But that's not quite what's happening, because
this is just, I agree it's not the same thing, but funny things like that can happen.
Yeah, here there's just a whole new Hilbert space living at that.
yeah. I mean, that point is really a point because of holography.
Yeah.
Otherwise,
Exactly.
it's an entire bulk.
Yeah.
Okay, fine.
Okay.
So what's the meaning of this line in the second figure? I mean,
This is the subsystem of the bath that I'm computing the entropy of. That's all. And the punchline of this diagram is that there's no island contribution when you compute the entropy of this. The answer is literally just the von Neumann entropy of this region. So it's just that formula that I wrote down 2 days ago. That's just the log of the length divided by the cutoff. Okay. Another interesting case, which I talked about briefly last time, is the extremal case, the temperature equals 0. If you compute, so I drew 2 things on the same diagram. So if you compute the entropy of R, just the boundary, so there's no left system now, then you find that that the quantum extremal surface is somewhere here. It's also outside. It's not at this point. It's somewhere, some finite location in Z. And if you
This is for which region?
the entropy of R.
Oh,
Okay? But also if you compute the entropy of the bath, you also have an island. So it's a pure state of the two. So it has to be complementary. Right? So that here we have a pure state of the union of right and the bath. And that's
this is really amazing. Right?
and this is manifested in that the R is dual up to this point here, and the bath has an island contribution there, and therefore it knows about the physics near the horizon.
And I suppose the size of that island depends on what? Probably just the boundary condition. The dilaton takes some value at the boundary. If you move that, you move the size. That's the only.
Yeah. And in fact, this location in Z goes something like phi times C divided by G Newton. Yeah,
Once again, the interaction between the field theory and the bath is crucial for this to be an arbitrage.
definitely.
It's hard to say what is field theory and what is bath.
Exactly. But you can turn off the coupling, and this will not move by much.
It will not go all the way.
No. The bath will still be dual to this.
When you say turn off, you mean now suddenly impose reflecting?
Yes, yes.
But doesn't that send some shock wave in so that
Yeah,
this
but
island now gets covered?
no. But in the models that I studied about for this kind of process, yes, you send in some energy E, which can be large, but the amount of entropy that you inject into the system goes as log E. So you don't actually change the entropy by too much, and because of that, you actually don't change the location of the quantum extremal surface by too much. That cares more about entropy than about how much energy you inject.
It stays extreme, sort of.
Yeah, exactly.
See, but then it's really strange. I mean, if you decouple them,
Yeah.
then you would imagine that and let's say you wait enough time, then you would imagine that the entropy of R, or that the region probed by R should go all the way to the horizon. The system finally is an extremal one with a Poincare horizon, and holography would say that you should probe the entire region.
No,
Otherwise, I mean, it's totally bizarre. You have a
I don't see why that has to be the case. So I mean, I turn it off here. There's some shock wave that falls in,
now your horizon.
and now I have a new horizon, something like this. So yeah. So now the extremal surface is going to be behind the black hole
Yeah,
horizon.
that's what I'm saying.
That's yeah. Oh yeah. Sorry.
Outside.
Oh, definitely. Yeah, no, definitely. It's outside the horizon, but it's still located here. The punchline, the point I was stressing is that there's still a region in the bulk that is dual to the
That's
the
right.
bath.
But that's sort of like the region behind the black hole in a thermophile double is dual to the other side.
Yes,
Not-
yes.
Yeah. Okay. No, this is fine. No, I would have been really. My mind would have been messed up if it was still.
Yeah.
It would have been.
You have a contradiction, exactly.
Okay, good.
But still, I mean, this is interesting. It tells you that these extremal black holes, the region far down the throat, can be influenced somehow by the radiation.
Yeah, if it were
But not the radiation, by the asymptotic region.
if it were initially in contact, etc.
No. So if I give you an extremal black hole, it is in contact, like in higher dimensions, let's say. Not, an asymptotically flat extremal black hole. That's what I meant.
Yeah. No, what I'm saying is
Sorry.
you can have, of course, the state, entangled with the radiation outside.
Yes.
And what's beautiful is that will show up in your way of geometrizing everything as an island.
Yes.
But perhaps you can also have a state which is not entangled. I mean, that's what you're.
Yeah. But before I get to your thing, so there's an observation that I don't understand yet. So it seems like there's a Hayden-Preskel sort of thing happening here, right? If I send in a message here, I lose it from R. This time, delta T, is not the scrambling time because we don't have entropy. We don't have thermal entropy. It just goes as G Newton over C phi R. I don't have an interpretation.
No, but if you literally do the chaos
Oh,
exponent at extremality,
Sorry. I think I have no, what am I saying? Sorry. Over G Newton. Yeah, it goes as n or n squared or whatever. I don't understand why this is what the interpretation of this is, but yeah.
But this is very interesting. Let me just mention one thing which I have to think more about, which is if you literally did the chaos exponent at extremality,
Yeah.
there is a interesting chaos exponent.
Okay, which is?
Which is not doesn't go like the temperature, but it exists because you have a blue shift after all. Anytime you have a horizon, and even the extremal geometry does have a horizon. So a wave which goes in and another which comes out have a huge relative boost.
Okay.
And so there's an interesting exponent there.
Okay,
but it's
okay.
not tied to the temperature, which is not there.
Okay,
So my
okay.
guess is it's probably tied
Okay,
to this.
that'll be interesting to check. Okay, thanks. Abhijit?
Well, an extremal one, in JT model doesn't require a charge per se, but okay, in the higher D perspective, yes, it would be charged.
No, probe. But the answer that you.
Oh, the probe is uncharged.
Abhijit?
Yeah, so this T equals 0, T not equals 0, why is there a qualitative difference between?
Why is there a qualitative difference? Let me see. I mean, isn't that always the case in GR when we study near extremal black holes and extremal black holes? There's always a sort of a discontinuous jump. That's
Single zero, double zero.
yeah, that's the.
And physically also it would make sense of it from the point of view of the boundary safety. Being zero temperature versus non-zero temperature. This hidden Pascal thing that we talked about is not present suddenly at non-zero temperature. Or because of this, the temperature will dominate this chaos response.
So the Hayden-Presco discussion doesn't seem to apply here, at least in a simple way, because I don't have exchange of radiation. But there's no Hawking radiation in this case.
Some little radiation will come out, right? As in,
What do you mean?
take the extremal black hole and you throw something in, it'll go slightly extremal, and then it'll settle back, and slightly non-extremal, and then it'll lose some energy to the path and then settle back, right?
Yeah, you can think about it like that. But I see. So you're saying in drawing these diagrams without throwing a probe, this notion of what is dual to what maybe is not that is not a very meaningful statement. But now you need to throw something in and see where that information is. But when you do that, you're now not extremal anymore, and so on. Yeah, maybe there's a way of phrasing it like that.
Work this case out. I mean, just to
Yeah.
So in this case, t is equal to 0. To start with bath, bath is not same as a Hawking radiation. Right? To start with, there was no Hawking radiation.
There's no Hawking radiation anywhere. There's a vacuum of everything.
So bath is just a different CFT, which has nothing. It's not no page time or anything, right? It's not after page time or something. It's just
No.
something that you're.
I didn't know what you meant by different CFT, but I mean the bulk CFT here is the same as the matter, the same as the CFT there. It's the same kind of theory. I mean, this is just the usual setup. We have transparent boundary conditions, and we have just one CFT living everywhere. Here it's living on ADS2 space. There it's living on flat space. Just the usual setup.
All this is coming from your 3D setup, right?
No, this calculation you can do in just 1 plus 1 using that formula.
No, but how? When I compute the entropy,
Oh yeah, sure. We'll get to that. Yes.
but that is the statement. Your statement is about the bath safety entropy, right?
Yes, but I'm applying this formula blindly. I didn't tell you where I got this formula. Well, I
I don't understand. So you have this bath,
yes.
and now what am I extremizing for the bath?
We'll get to it. We'll get to it. We'll get to that in a few minutes. So the last case, which is what I call a stable Unruh state, where you continuously feed the black hole with pure matter. Okay? So there's some Hawking flux that's coming out in a thermal state, and you imagine balancing that flux with a pure state. I believe you guys studied something like this, yes. And in that case, you find that so if you compute the entropy of R, you find that the extremal surface is behind the black hole horizon. Okay. Yeah. So it's the same geometry, but it's located behind the horizon. And again, the time difference between the sort of infalling time of this point and the time here is a scrambling time, as I wrote down over there. Okay. Any questions about the recap and the examples?
And just what is the significance in 5 for the fact that it lies inside? When it lay outside, we said, look, there's some region outside the horizon which is actually encoded in the radiation.
Yeah.
And here, I suppose there's some region inside which is encoded on the L or R boundary. Is it on the R boundary?
Yeah. There's no L anymore, right?
Yeah. So on the R boundary.
Exactly. So this region behind the black hole horizon is dual to the bath.
Sorry, one last question.
Please.
Briefly. In your internal setup, if you were at t equals 0, well before page time,
Yes.
then I should think of the whole universe.
What am I computing the entropy of?
It's a question about how I should interpret space-time.
Okay.
So, should I then interpret the degrees of freedom behind the horizon as being made up of the L and R?
The region behind the horizon inside the Wheeler-DeWitt patch of those two times Yes, it's dual to R. It's dual to LR.
So it switches what? That's not. Yes.
Yeah. I've been calling that property the fluidity of the ADS CFT dictionary. Depending on the situation, things can be dual to one region or another.
You mean it switches between LR and the bar?
As a function of that.
Yeah.
But, Emma, just
Yes.
to go back to point 5,
Yes.
the fact that the R boundary encodes for the region inside the horizon. Now,
The R boundary encodes something which is inside the horizon. Is it? Yes.
I mean, that should help vis-a-vis the bulk reconstruction story for the inside, right?
Yeah, but I don't think it buys you anything really, because you could have just said, let's consider a pure black hole in ADS. Well, if I give you the entire CFT, well, that's dual to the inside. But just saying that statement doesn't really help you.
Saying that, no, but now you have a proof of that, namely, presumably as you throw more and more in, as the duration for which you feed the black hole increases, you might access more and more of the region inside.
Well, but I would agree with everything you just said, though I would say it still doesn't give you an explicit dictionary.
It doesn't give you an explanation.
That's my only complaint.
To it, perhaps.
Yeah. Okay. So now let me talk about this 2D, 3D example. This is the paper with Juan, Raghu Mahajan, and Ying Zhao. And so the idea is to take the same model that we've been studying, but replace the CFT coupled to JT gravity with a holographic CFT. So this means that the matter sector of this theory is dual to a new 3D bulk in which
Really sorry, one last question.
in which we will compute the entropy of the radiation using the 3D RT formula. Yes, Sandeep.
Yeah, I'm really sorry.
No worries.
So just to plant the thought and then we can come back to it, although you started with ADS to this, that, and the other, but then as you yourself said, well, you added the radiation bath or whatever, and that was a caricature for the asymptotically flat region. Couldn't we try to do some of this when you embed it in 3D, etc., just for a Schwarzschild-like black hole?
In principle, yes. Although I will maybe touch on some subtleties about that. Okay. Okay. So now, so we have JT plus holographic CFT, and then which will be coupled to holographic CFT bath. Let me call it like that. Okay. So now, what would the 3D geometry look like? Now, if I give you a holographic CFT, so let's go through this step by step. If I give you a holographic CFT on some metric G, let's call it G2, Ij, then the 3D dual must satisfy, the 3D dual geometry must satisfy the following boundary condition. That on the boundary, this thing goes as something like 1 over epsilon squared, this is like the cutoff, times G2 Ij, where these I and J's run along the boundary directions. If you recall, when we were studying this system, there was this convenient coordinate W in which the state of the CFT was the vacuum, right? So we had something like this. It was a vacuum in Minkowski space. W plus minus with the flat metric, right? So minus dW plus, W minus. And in this coordinate system, the 3D bulk is very simple. It's simply Poincare ADS3. So plus minus plus dCW squared divided by CDW squared. So we have a picture that looks something like this. So this is a time slice here, and the direction going down is the new holographic direction, ZW. Okay? Now, all that's left for us is to determine the location of the cutoff surface, or sort of the physical cutoff surface corresponding to the working with the physical coordinates. And you can locate that in the following way. So for the ADS2 region, we have, so you equate this metric factor or term with the following. So this comes from this boundary condition here. And this gives you it gives you ZW as a function of x plus x minus. Is this clear? So this is how we find the new cutoff surface, and we do something similar for the Bath region. So there's the ADS2 region, and then there's the Bath regions. You do something similar where you equate this with, I guess, 1 over epsilon squared. Yes? Good. Then you get a picture here. So this is ADS3.
That's the same as just choosing the right conformal factor.
Precisely. And then you get something that looks something like this. Okay. So these are the Bath regions, and then here we have the ADS region. Okay. So here you have to use the coordinate transformation between W and X plus, or W and Y. W and X and W and Y. That coordinate transformation is what keeps track of the stress tensor that moves about in this spacetime. So really you're keeping track of this. The location of the cutoff surface keeps track of the state in some sense. Okay. Good. Now, let me give you, let me see.
And as you said in your first lecture, this conformal transformation keeps T equals 0 in the bulk, but induces T non-zero outside.
Correct. Okay, so now, I don't know where no, let me draw it here. Let me draw it again.
So now that you have a holographic CFP,
Yes?
your central charge is really 1 over G.
Correct. No. So I'm working the following limit. 1 over G Newton is much greater than C, which is much greater than 1. I imagine that so I use this to work in the semi-classical limit in 1 plus 1 dimensions. I use this to ensure that the new holographic theory in 3 dimensions has a large n, or this theory has a large n, large radius dual.
I think Gautam's saying there's a 2-dimensional G Newton and a 3-dimensional G.
Good. So this thing is like LADS 3 divided by G Newton 3.
So this is like Randall-Sundram.
Yes. Except usually, so I guess there are many versions of Randall-Sundram. Often people relate the 2-dimensional G Newton on the boundary with the 3-dimensional G Newton by this relation. So you don't actually have this much greater sign. You'll have this is roughly this.
Yeah, that's right.
Yeah, but here we're adding a new term on the brane, and so we're adding a Ricci scalar term with a different G Newton, which is much smaller than the induced G Newton.
And what are you doing to make gravity dynamical in the 2-dimensional?
That's what I just said. We add we explicitly add by hand a Ricci scalar term. So there's
Yeah, you add that by hand. Often we do ADS
Yeah, yeah, but here we integrate over it.
So I wanted to understand how you made that passage. Freezing is not the same as integrating.
Yeah, I never said I was. It's the metric on the brain is definitely not frozen.
Yes, but I'm saying often we do ADS-CFT.
Yes.
In any case, we freeze.
That's right.
Yeah,
That's
you're
right.
not freezing.
Yes.
I want to understand how what.
The way we sort of thinking about it is so we have first I CFT on some back.
Alternate set of boundary conditions.
I'm telling you sort of how these alternate boundary conditions are imposed. So we often do something like this, right? And so we just study this theory with fixed background metric, and then we add IJT, J and phi, and then we path integrate over Gij. So there's e to this blah, and then in the path integral there's a variational integral. So we integrate over Gij and also over the dilaton. So this implies that we're imposing some sort of Neumann conditions on the metric.
Yeah. Now, if we try this in n equals 4 angles, we probably hit a
Contradiction.
contradiction.
You mean like?
Integral would be sort of empty because it's not normalized.
Can I just make a comment which is, and we can come back to Randall syndrome, but normally what we do is when we do ADS-CFT in our minds, we take the boundary in the end to go to infinity. That is, if we work in Poincare coordinates, we take z to go to 0 ultimately. But if you get z at some finite value, let's say small, then you won't decouple the non-normalizable mode because there'll be a cost for exciting it, but you can excite it.
Right.
And I think that's what they do here.
So this epsilon is finite.
Exactly. That was my next statement. Yes, we are working with a cutoff.
Fine.
Yes. Yes.
Then why aren't you also integrating over the metric on the field theory?
That's a choice, right? I mean.
No, but that's an important point. Somehow you're not keeping your cutoff epsilon.
Oh.
It's finite here and
No. It's finite everywhere. I guess that's how you'd have to work with it.
but then also I don't see why you wouldn't have dynamical gravity in the bath region.
No, I mean, it's a choice, right? I mean, I can choose to integrate over whichever part of the boundary metric as I want.
No, and if furthermore, if there were boundary dynamical gravity in the path, then because one is ADS to other is flat, there would be a question of vacuum bubble and some domain wall and some the ADS is being of the whole flat space.
Well, then whatever happens will happen. I mean, the point is, from the ADS3 perspective, you have the choice of where the boundary is located, but after that, what the system does, it does, right? I mean, what I don't understand is what Shiraz was saying. I understand that you may choose to locate the boundary at some finite z, but after that, how do you ensure that you don't have gravity in some part? That I can understand.
Can you say a little bit about why you said that this is tantamount to having finite epsilon?
I'm just saying that.
M2 gravity.
Yeah, I'm just saying that suppose you located the boundary of the ADS region at some finite z, then what we are calling the non-normalizable modes, if we excite them, we do that at some finite cost in energy. So actually this is really what happens in the D3 brain system. Because the asymptotic region doesn't decouple, right? If you keep the one in the harmonic function. And so what really happens is that you have ADS5 for some range of z, and then before you get to z equal to 0, the corrections to get to asymptotic
Yeah.
come in. So I'm just
Let
saying
me-
you can do that here, and then the gravity in the asymptotic region of the D3 brain system would show itself.
Let me postpone this for a few minutes. Okay. So this is what our system looks like. Let's consider a time slice. Doesn't matter which one. Now there are three ways of interpreting the system. The first one is sort of what I call the no gravity perspective, where I have, so maybe I should write down PL, L, I have a,
Just one question. It doesn't y in fact
No, there's an additional cutoff in the ADS2 region, right?
Yeah, but suppose epsilon were to go to 0, would the wild factor blow up then?
Yes.
Maybe that's it. We'll talk about it.
And defining, I should emphasize that in defining the theory, yeah, here we're also imposing that it's ADS2 near this boundary, right? So it's ADS2 near the boundary of ADS3, but it's also ADS2 near the boundary of ADS2, or near this region here. Okay. So as I was saying, there are three sort of points of view that you can take for viewing the system. Okay, so one is but I want to hear what he said. That's the problem. I'm going to draw a picture, which I think is actually going to emphasize what you're just saying. What I didn't hear you say, but I think. So one perspective is the following. I have these two holographic CFTs coupled to these holographic quantum mechanical systems, or these defects living on the boundaries. The second perspective is the purely 2D perspective. So I'm going to draw it in this way. So here I have a holographic CFT. I drew it as a sort of bent down like this because it's to make contact with the next perspective. Here I have JT gravity plus holographic CFT. And here I have holographic CFT. And then there's the third perspective, which is the most interesting one, where you replace the holographic CFT here with its three-dimensional dual. So then you have, again, something like this, where here I'm going to call this this is a UV brane, so the usual kind of boundary in ADS CFT. Here's another UV brane. It's a non-dynamical brane. But here I have a JT brane, a JT theory on a Planck brane to make contact with Randall syndrome terminology.
And this picture is a picture of the conformal factor, effectively.
Effectively, yes. Yes. But in this bulk theory, we have dynamical gravity here, we have dynamical gravity here, but we don't have dynamical gravity here and here.
Because that conformal factor is not infinity.
Yes. Yeah. This line and this line are much farther towards infinity than this guy.
That was, I guess.
Yes. Yeah.
Physics.
Exactly. So now, in comparing the first picture and the third picture, you should think of so this system is dual to this entire bulk plus this brane.
So, but do we know of examples of ADS CFT where you do put this finite cutoff and let the gravity fluctuate and it's a very stable reality?
I think so. Yeah. These Randall syndrome models. Yeah.
But there it's interesting.
It's been analyzed, and some situations do make sense. I'm no expert in that. Maybe Shiraz knows more about Randall syndrome.
Is a very solid thing, right? But when you let
How?
this brain fluctuate, I just saying that this is now beyond the realm of standard ADS CFT, where your boundary is now fluctuating with the finite cutoff and so on. So do we have evidence to that effect that this is an established correspondence?
I think this is going to be better than ADS. Because there wasn't even a boundary. It was really just a field theory. That boundary is being made by dynamics. This feels good.
Which boundary?
That fluctuating boundary should be fluctuating because there wasn't a field theory.
There wasn't a field. Sorry.
The real is the first one, is
Yes.
number one.
Yes.
That's what the boundary should tend to.
Yes. Yes. Yes.
And it tends to that. Everything in the middle is dynamic.
Yes. Yes.
It's a holographic dual for the
First one.
first one, which is totally concrete.
Yes, which is real field theory.
Yeah, I've been calling this, so this is sort of holography within holography. I've been calling it holographic inception.
This is like a holography of the boundary. If you have a CFT with a boundary, its dual would be of this type.
Yeah.
So, just to, if I understand right, if I just take a surface in the bulk, so let's consider 3D gravity. If I take a surface in the bulk, and if I could do some sort of a reduction of 3D gravity on that surface, on the JD, the blank plane which you're saying, will I get JD gravity or the theory of gravity on that?
Good. So that's actually a separate question from the case I'm considering. But so I'm putting in JT gravity by hand. Okay, that's one point. Second point is so the question you're asking is, if I don't put that in by hand, would I get? So I will naturally get some induced gravity on this brain.
Yeah.
The question is, how does it look like JT gravity? If I was to make a guess, I would say yes. But I did do some analysis of just start with ADS3 and put a brain and study the fluctuations of this brain, just the equations of motion governing the fluctuations, and they look a lot like the JT gravity equations of motion. So let me have, yeah, so there's something like that. Okay. Okay, now that Shiraz feels good, now let's use this thing for something good. Okay.
Just to say, there is one, still some vestige of that, the value of the dilaton at the boundary will remain sort of at the demarcation of the region where gravity is
Yeah.
dynamical.
That's right, that's right.
And somehow, in how that value, there has to be a 3D holographic interpretation of that. If
Yeah, sure, yes. I don't have the answer to that though, but yes. Okay, so now,
It's just to say it looks very beautiful.
okay, that makes me happy. Now, let's say we compute, so now let's use the 3 dimensions to compute the entropy of various regions on the boundary. Let me see. Okay, so let's first talk about the following entropy. So say we want to compute the S bulk of the region that this sigma LR that I've been calling in these previous lectures. So the entropy of this subregion. This subregion is this subregion in the second picture. In the third picture, this entropy becomes geometrized. Right? So it's an entanglement entropy here, but now we can compute it using the RT formula in 3 dimensions.
Which one? LR.
Sigma LR, sorry, okay, maybe I should write this down. This is important. So the thing that we're computing, okay, so we want to compute the entropy of LR, or we want to compute the entropy of SBLBR, okay? From this 2-dimensional perspective, so, or rather from the 1-dimensional perspective, LR and BLBR are complementary systems, okay? Now, when we compute the entropy of either system, LR or BLBR, in the 3 dimensions, it will be automatic that the entropy of one is equal to the entropy of the other. That's imposed by the minimality constraint in 3 dimensions.
Feature of the RT form.
Precisely. And so, but for now, let me just use the language that I've been using when computing the entropy of LR.
When it is already assumed that the full is a pure state.
Yes, it's a pure state, exactly.
That's an assumption, additional assumption.
No, that's not an assumption. We considered a pure state. Yes. So one contribution to the entropy was just the S bulk of sigma LR. Okay? That's this region. Okay? And what does it look like in this picture? I'm going to draw the. Say that again? Not yet, not yet. So this was the trivial surface that did not have a dilaton con. Well,
This is not the whole integral entropy of K-ln.
this is one contribution to the whole. No, so one possible. For some reason, I can't get the right words. It's the entropy evaluated on the trivial surface for the entropy LR. Okay? There's no dilaton contribution in this case.
And this S bulk is, so one contribution to S bulk would be this matter fields, the CFT matter fields in the gravity. The other one could be the gravitons, but then the gravitons are neglected because of this limit.
Yeah, exactly. So the other thing could be dilaton over G Newton. I'll get to this. Okay. So in this picture, let me also draw the cutoff in the W coordinate. Okay? W coordinate cutoff was I meant the asymptotic boundary of ADS3, the actual boundary, something like this. Okay. Now, when we compute the entropy of this region, it's just one interval in ADS on the boundary of ADS3. So that means RT surface just looks something like this.
That cutoff just goes all the way on the non-dynamical part or not?
No. Yeah. Ultimately, you take this epsilon to 0. Well, this epsilon is different than that epsilon. Yeah, you do. Well, I'm actually not entirely clear now on this. So you can take this thing to 0 while this thing stays finite. So exactly. So there's this epsilon here which you take to 0 at the end.
Is it the same also? Or is it
Um,
on the right hand side? Why are you deleting this?
Just to say, the dilaton is a non-trivial part of the story. I just want to say, because you see, the dilaton is growing towards the boundary of ADS3. So while you take the relative conformal factor
Yeah.
between the two regions, to go to 0 or whatever,
Yeah.
you do something very careful to
Yeah.
the
There's a funny.
The only reason I emphasize this is, sorry,
Yeah, please.
You're going to now get the entanglement formula from, do you talking about in 3D, you're going to add in a dilaton contribution. And it would be nice to understand that from the 3D perspective.
No, we do understand that from the 3D perspective. I'll get to it.
Okay, I
Yeah.
thought you just get the C
No.
6 log analog.
No. I'll get to that contribution in a second. But yeah, I think there's a way that you can take this epsilon to 0 and the epsilon in the ADS2 thing to 0 or to 0 in the right way. That this thing goes to, that you can think of this as approaching this boundary, but this thing remains in a finite location. That's how I'm thinking about it. But we can maybe talk in detail after the talk. Yeah. So the entropy of this region is just the RT surface that looks like that. What is this formula? So first of all,
From 1 to 3,
it's good.
not 2.
Sorry, say that again.
If I think of this, which is a nice picture, from
Yeah.
1 to 3,
Yes.
then the entropy of the HQ, L and R, why is this given by this?
Good. So the entropy is just going to be equal to the area of some surface. Area of, let me call it sigma 3, LR. So it's the area of the minimal surface, right? So S is equal to, or extremal surface. So you extremize over all surfaces, sigma 3. It's a codimension 2 surface in 3D that is anchored to L and R. This is the RT prescription.
Just a little bit outside and a little bit outside.
Let's take a little bit outside, a little bit.
So that I would interpret as BLBR in a standard way.
No, XLR.
I'm computing the entropy of this region. But it's a pure state, so it's also the entropy of the complement. So it's true.
No, no, but I mean, I don't know the rule is when the boundary is a corner and where you anchor, where you anchor the surfaces and so on.
So just a little bit one side of the corner and let the other guy.
Yeah, I thought that was clear when I drew it here. So yeah, so as Shiraz was saying, let me do something like this. Okay, which in this picture is like something like this. Okay. And now this thing anchors on these two, but I'm just taking the limit as it's very small.
But then why is this not two pieces? So one from that part to that and that part to that.
Sorry, you said to that. What is that?
The cutoff to the L and the cutoff to the R, the separate pieces.
Cut off to the L. You mean something like this?
Yeah.
This is.
If you want to compute entropy of what you are having enclosed in the picture one. So in picture one you have enclosed the L with a bracket a little bit and R with a bracket a little bit. And you want to compute the entropy in that picture. Then you just can compute that entropy with the small r's.
But the rule for the RT surface is that has to end there.
Yeah.
There's no other rule for the other end, because there's nothing else that surrounds it. So it can
That's
do
right.
whatever it wants from that point of view and from that point of view, and it chooses to join up. It could have chosen to join up on that JTH CFT as well.
That's right. That's right.
It's up to it.
Sorry, you're saying if you have the RT surface anchored at the ends of the two square boxes,
That's the rule.
it does anything.
It does whatever it wants. There has to be one end here, one end there, and then it does whatever it wants. And
So-
it could choose to meet up. There's no other end at which it has to.
So the point is that, so good. So where can RT surfaces go? So they can either end on the endpoints of your interval, or they can end on any defect in the bulk, which is like some sort of brain or end of the world brain or something. Which in this case we have such a thing, which is the Planck brain. Okay, so it can potentially anchor there, and the question is whether, if it anchors there, does it get pushed all the way to this point or not? Effectively, I think that's sort of your question. We'll get to that case in a second, but for now, let me say that the thing that computes this entropy is this RT surface. It's the one that goes from here to here, and it manifestly there's no dilaton contribution, right? It comes purely from the geometry in ADS3, which we know from intuition of applying RT formula usually, that captures the matter entropy on the boundary.
What would have been the difference if in the picture of 3, if you really had a fixed metric on the boundary, on the whole boundary, including the 2D.
Yes.
If you had that and you asked for an integral entropy for this region, you would have got this surface.
Exactly. So this contribution doesn't care about the JT region. Let's talk about the other contribution.
This could even hang, right, inside the bulk.
Hang, you mean like do something like this?
No, just like that. Stop.
No, it can't stop.
Like the 2D case.
No.
The 2D case, this point was just a bit inside.
No, it can't. No, it can't stop. It needs to be homologous. It needs to be homologous to this region.
No, but that region is not present in one.
Well, that's the thing. So this is why this is a bit confusing. I think you should think about the simplest perspective to take, that the bulk is dual to the field theory on this thing. That's how you should think about it. Okay. So there's some field theory living on this line, and we're just computing entropy in the 3D dual of that field theory, and we're just applying the usual rules.
But if you think about it from the one point of view, then the part homologous to that interval would just be an interval inside. From the square bracket to the dot.
No, but this is also homologous.
It is, but I'm saying it could also hang, right?
But hang where? So where does it go? Tell me where it is. Just stop there, here?
And then it's in the
No, this is not homologous.
to the one picture.
Yeah.
One. Homologous to that interval, right?
No. So this point is here. This is not homologous to this. Homologous means that the RT surface and the region that you're computing the entropy of are the only boundaries of some bulk region.
You know, if you don't mind, you know, the bounding surface does not have an end point on the other side. So if you've got to be homologous, you should not have an end point on the other side.
Yeah, that's what I'm saying.
What is the effect of?
This is not homologous. Let me-
that L quantum mechanics is not the boundary of that.
It's not the end point because you have to go to the other side of the boundary.
Let me
It's like an open set.
let me give you something which is homologous to that. So let's ignore the other side. Let's say we're just literally just computing the entropy of this, of this thing, just one side. Then the only thing you can have is something that ends on the Planck brane. The reason why this is homologous is that I can now deform this all the way to this point, or I can deform this all the way to this line. And that's why it's homologous.
I thought you were going to say because then the bulk region in between has two boundaries, one which you drew and the other one up to the point and including part of the Planck brane.
Yeah.
But the part of the Planck brane is part of a fluctuating metric, so it's really not in any sense a boundary.
Exactly. That's another way to say it.
But up to you.
This surface, how would it matter if I just take a 3D gravity and 2 points?
Are we talking about this surface or this surface? The first or second?
So let's say it's in the second picture.
This one?
Having this the JD plane.
Okay, okay.
So the conformal factor tells me how to embed JD plane in the 3D picture.
Yes?
But instead of that, let's say if I had just a straight line, the complete flat,
Yes?
how would the contribution would have changed?
It would not have changed.
It doesn't matter
It
what.
would not have changed. It would not have changed. What would change is the next thing I was going to write down.
Before you write that down, because I know what you're going to write. Because now the dilettante comes in. Just to ask you, from the sort of Randall, Sundram, whatever perspective, if you just had standard gravity in 3D in the bulk,
Which we do, okay?
right? Is there some way we can say that you actually get JT gravity, dynamical gravity on the boundary?
Induced or put in by hand?
Well, I mean, the spirit I thought was that once you decide to locate the boundary in some finite region of the wild factor or whatever,
Yes?
then you get what you get.
No, so I agree. There will be an induced part, but in our case we're putting an action in by hand.
And that's
but-
the part which worries me. because
Sure, yeah. It might worry you, but let me say first. Let me make a few points. First point is that because of the limit in which we're working, which I erased, that the G Newton G2 is much less than G3 over LADS. 3. Because we're working in this limit, the term we put in by hand dominates over the induced term. Okay, so that's the first point. Second point for why this is fine to work with is that the two-dimensional theory was sensible. So we expect the 3D bulk to also be sensible.
But I mean, just to understand, what in the 3D bulk dual cares about the extra 2D gravity of induced on the boundary? You might think something should change. Otherwise, you know.
Yeah.
Surface will.
Right. What?
That floppy surface, how it vibrates will get.
Yeah.
Because its action is controlled by this extra term. This counter term makes it.
It would mean that in the two-dimensional theory, the central charge of the field theory is comparable to the two-dimensional G Newton. So working in the semi-classical limit won't actually be sensible. So
Can I make one more? I mean, if you're trying to go from 1 to 3, the information of what that field theory was at the tip of the boundary has to enter the picture somewhere.
Yeah.
This is where it's coming.
There's a Hilbert space sitting at that HQM. Separate Hilbert space.
that's right.
See, all I'm saying is that maybe you will say that the way to do it is to saying is so far we haven't introduced that extra information, right? The information of the HQM, which is tied to the dilaton, etc. Because the HQM is dual to JT gravity, right? So that information has to come in somewhere in a holographic dictionary.
Yeah, and he's putting it as a counter-term contribution to the boundary. He's saying that the action in the bulk is what it is, and the action in the boundary has an extra counter-term piece,
That's,
which is JT gravity.
that's right.
We don't know of any example like that.
I know. I mean, you're inventing your rules as you go.
Yeah.
That's okay.
All I'm saying is this is an extension of
Right.
this.
Although I did complain about that to Juan. This seems, I think what you're saying is that this is not conventional Randall syndrome. But he said, no, people have done this, and then as in put in terms by hand. And it's apparently a thing which is lumped in with Randall syndrome literature. But
If the only justification was that this has been done by Randall Sundaram, I would not be too happy. But, but this seems better than me. Right.
This
Good.
is this whole Takeyanagi, it's in your paper you said Takeyanagi and so on. Rain story, is it?
No. In the Takenagi story, they don't put in an intrinsic dynamics for the brain. Yeah.
If I look at this surface, then there is dilaton and there is matter field, but there is an information about the surface.
There's a?
There is an information about the surface, which you can either think about that the surface is flat and the information is in the QM on the boundary, or you can think about that there is some information on the boundary itself.
Okay.
What is that information going in? I do not understand, because there is some information in the conformal factor.
Yes.
Between.
Yes.
And how is that conformal factor affecting your answer? Because my
My
matter
answer?
field is living in non-trivial background, which is this conformal factor.
Okay. So all the information about the dynamics in this state or how the state evolves comes into this function of how the cutoff evolves in time. So this contains all the information in some sense.
Yes, one way of thinking about it, about the cutoff in boundary of ADS2, how you cut off your boundary of ADS2. This is one way of keeping track of that information.
Okay. You meant ADS3 or did you mean ADS2?
ADS2. So
Okay.
either I think about it that I have a pure ADS2 and my matter field and the dilaton is living there,
Yes.
or I think about it is not a pure ADS2, rather there is a black hole and on top of it there is a matter field. What is the information about the fact that there is a black hole and the matter field is living on that? This surface looks like that it is living on the ADS2.
I think we will get this kind of information when considering the other contributions of the entropy. So let me get to that.
That will be just a dilaton, no?
Yeah. But let me get to it. Also because Abhijit needs to leave. I'm almost done. So at least with this part. So there's another contribution, which is let me draw it on a different slice. Which is
Maybe we have a moratorium on questions after.
okay. Phi of XL, phi of XR, plus S bulk of the union of LXL sigma RXR. So this thing is sigma LXL sigma RXR. This is XL. This is XR. Okay. So now the question is, what does this thing look like? First, let me just write down what this contribution looks like. So the entropy. So the dilaton terms come from contributions somewhere here and here. The S bulk term, this is the entropy of the following subregions. I guess there's dilaton here and here. Maybe that's how I should draw it actually. So in this picture, we have dilaton here, and we're computing the entropy of the union of this thing and this thing. And there are two possible ways of computing the entropy. of the union of these two regions, we can have the surface that either, so there's this surface, right? Or there's this surface. Okay? Notice, so let's ignore the second one that I drew. This surface can never be minimal, this contribution. Why? Because it's always larger than the trivial surface. Okay? So I'm going to ignore this surface. So, no. So the trivial surface is this. Now in computing this entropy, this thing, one possible surface is a union of this plus this. So there's an additional term, extra, in comparison to the trivial surface. So this will never be minimal, so I will ignore it. So the
So in 2D, when you were talking about this formula, and you were pointing out this point which is extremizing this distance, how did you compute S bulk?
I secretly computed it this way. Although you can compute it generally with as a general function of the cost ratio, and you can extract some physics from that. Okay, so we have now the competition between these two surfaces. Now I'm just translating this statement into 3D. Okay, but
Is that, apart from the area, is that a special contribution from the end?
this,
Yes.
yes, the dilettante. Well, for now I'm just applying this, and it seems to say that you should extremize the area of this extremal surface. So this is a bulk extremal surface by itself. You should extremize that plus the dilettante, and this. So basically, by moving this point around, that's how you do it. But let me emphasize again. Let me emphasize actually that so this is something new. That this is actually already contained in the standard HRT prescription. Usually when you have a boundary in your bulk, the cases that people often consider is when that boundary, or like an end-of-the-world brane, is non-dynamical. So you don't pick up anything from that. But if you have an intrinsic Ricci scalar term, or intrinsic dynamics, then you do actually, in fact, pick up an area term. And this actually follows from the standard discussions of HRT and the proofs thereof. Yes. You have to you pick up an area piece from that thing, and in this case the area piece is just a dilettante. So this is really here we're literally this thing follows entirely from HRT or RT in 3 dimensions with a dynamical brane. I wanted to emphasize that.
Just to understand the point, so if you have a dynamical brane at which the HRT surface were ending,
Yes.
and did you mean to say if that brane had some area, it was rapid, then you would include that area? That
No.
you would do.
No.
You mean if there was an induced gravity contribution to that? Is that what you meant? Just to understand your point.
So I'm not sure about if it's induced.
Okay.
Maybe that's the same thing. If it has an intrinsic Ricci scalar term, if it has intrinsic dynamics, like in this case we have the
For gravity, right?
for gravity. That's what I meant. Yes. Here, for example, we have the action on the Planck brane, phi times r plus 2 or whatever, and the coefficient of r gives you is the entropy.
Or could you, just to understand it, if, for example, this was the spherically symmetric sector of a higher dimensional system in the first place, that is your 2D system you started with, was secretly 4D, with the dilettante being the area of the ST, then would it simply be that when you go to 5D, in a sense, just the area of the HRT would automatically give you the
I think so.
dilettante
I think so.
without having to, add it in by.
Yes, I believe.
Seems like that should
I believe so. Would you have a question?
No, this case that you were talking about essentially is when, from the just boundary point of view, at boundary live extra degrees of freedom, right? Then you will have that kind of thing.
I mean, when working in this picture, we're not saying that there's a boundary with dynamical degrees of freedom.
No, I mean just if this HRT formula that you are talking about and this extra contribution that
Yes.
So that would happen if you have some extra degrees of freedom living at the boundary of the CF. correspondingly you
Yeah, yeah, yeah. Yes,
the gravity dual of that boundary CFT.
I see. Yeah, yeah. Yes, yes. Okay, so now everything I said applies equally to LR or to BLDR, right? So all these surfaces are actually homologous to the bath. Take, for example, this guy. The bath is here and here. And indeed, this the bath union, this thing bound the entire ADS3. Okay, so they are homologous. And
Extra boundary from the ends of the path or
well, it's infinity, right? So I mean, there's no
so it doesn't contribute anything.
no. There's no boundary there. Is I guess what I'm saying. How about this? Think of it. You can think of this as wrapping the cylinder. Now there's no boundary there. And also, this surface is also homologous to the bath because I can take these points together. They meet. Then I take it off of the brain, and again, it's the same thing. Okay. I'm just saying this thing and this thing are both homologous to the bath. At early times, this surface dominates, and therefore the left-right quantum mechanical systems are dual to everything inside this region by ideas of subregion duality. But at late times, this surface dominates, and the bath is dual to everything up to and including this part of the Planck brane. This region here is nothing but this region here. So we see how in this picture, subregion duality in 3 dimensions implies that the interior of the black hole is dual to the bath. It's contained in what is called the entanglement wedge of the bath. Yeah, and a few more comments. So here,
Abhijit has to go, but after this, just go over what you just said because I don't fully understand the statement of subregion duality as well. So,
okay.
remedial short.
So
Including questions or comments.
my final comment was that just for Abhijit, I'm going to truncate it. This is ER equals EPR. Done. Okay, good. Okay, thanks.
Say again. So
Yes, I'll say. So first of all, subregion duality is the question of which part of the bulk is dual to which part of the boundary. It's been proven that that the entire entanglement wedge of a region is reconstructible from that region. Okay, using these ideas of quantum error correction and so on. Okay.
proven anyway. Okay, fine. I mean, it's conjecture.
No. It's
The proof.
well, no. What?
It's a semi-classical.
No. Good. So these are statements about some fixed background. There's a subspace about what people call a code subspace. So you have a fixed background, then you consider a set of states around that. You excite the quantum fields there. You don't put in too much that the region fluctuates, and within that subspace you can establish a duality. It's in the same subspace in which this JLMS relation applies. That bulk relative entropy is equal to boundary relative entropy. Okay.
And when you say proven, does it go? If it were the causal wedge or something inside, then you could just take wave packets and see their image and so on.
Yeah, good.
As whatever various people did. And here, since it's the entanglement wedge, which can extend beyond the causal wedge, I guess.
Yeah.
The proof consists of.
Good. So there are two.
Just to understand.
Yeah, there are two routes. One is just to use this quantum error correction technology, which is very opaque, but it nevertheless does give you a one-to-one correspondence within the subspace. The second, it's also working in the second idea is also working within the fixed geometry, this evolution via the modular Hamiltonian of Lukowitz and Faulkner. So they extend the HKLL prescription, which is a purely causal wedge notion, to something involving modular flow, where you evolve with the modular Hamiltonian, and that can give you access to things inside the entanglement wedge.
I see. And this is a modular Hamiltonian in the bulk, is it?
Well, so there's an identification, right, of the modular Hamiltonian on the boundary with the modular Hamiltonian in the bulk, plus the area term. Or sorry, other way. Sorry. Modular Hamiltonian on the boundary is equal to the area term plus the bulk modular Hamiltonian, which by that I mean the modular Hamiltonian for the bulk quantum fields. Yes. So you evolve with one, that means you also evolve with the other, and you imagine that the area term doesn't do much. It only it just sort of evolves you near the RT surface.
I see. Okay. Thank you. And now coming back to your thing, just to understand that point 3 there, if your minimal area is the one which ends on those two dots, then the path will have access to the entire region on the outside,
And this,
including up till that line.
yes.
And then why does that somehow, but not the region, between the, to the left and right, between the upper cusps or whatever, right?
This region?
Absolutely, right?
This region is dual to LR, right?
That's dual to LR. Just to, sorry to be so dumb, why is that dual to?
Because this is the entanglement wedge of L, and this is the entanglement wedge of R. Or, sorry, the union of these two regions is the entanglement wedge of LR. So by the same reasoning. Yeah. Again, this picture is an extension of this picture in 3 dimensions, right?
Yeah.
At this point, yeah.
I understand.
It's ending at a point like in 2D is because the region we are considering on the boundary is also a point. Is that the thing? I mean that
Sure.
right?
Yeah.
And see, so if I consider a 2D picture, the quantum extremal, the region X is going through the GT, right?
The point X, you mean?
Yeah. So
Is on the GT brane, yes.
the region is through the plane, but if I just allow it a third direction, it's giving you this thing.
Yes.
Computationally, how does so both of these things compute the same thing really, right? The answer is the same for
So over here, the answer is given by the dilaton plus the entanglement entropy of this region.
yes.
Now let's translate these two things into the 3D picture. The dilaton is still the dilaton, right? It's not holographic. It appears in both descriptions. But the entanglement entropy has been geometrized in terms of this RT surface.
Yeah.
So now we have, the entropy here is the sum of the area of this plus the area that you pick here, which is the dilaton.
Area in the sense it's still the one.
Yeah, one-dimensional area, which is just the
So
dilaton.
I'm just saying there are two. It seems that there are two one-dimensional surfaces. which are
Two one-dimensional surfaces?
Yeah, in the picture 2 and picture 3.
There's only one, it's just, this point is the same as this point. So it's just one thing.
Yeah, so I'm saying the two lines which are in the picture 3, one on the GT brane extending from.
Oh, you meant those two? Or, okay, let's ignore that.
Let's start from a left point to a point on the brane. Yeah, so there are two lines connecting it. One is going through the JT brane, one is going through the 3D space.
So which is the one going through the JT brane? You mean this thing?
The older one, yeah, exactly.
No, this is the cutoff surface.
No, but that essentially gave us the same thing, right, before, in the picture 2. That is exactly what we were computing to,
The entropy of.
entropy of.
Yeah.
So I'm just saying that now you have two surfaces which seem to give you the same entropy.
No,
One of them you're doing a field theory calculation.
yeah.
Third one is the RT. Here you're just computing an area.
Yeah, exactly.
So it has to hang outside.
On which you are calculating independently, you have matter degrees of freedom, and in addition you could have a fluctuation of 2D gravity for formal factor. And is it that the contribution of 2D gravity fluctuation factor is subdominant in this limit?
Yeah, definitely. Because the gravity is just one mode. It's much, but we have large C.
So, I mean, sorry, but you already answered this, I guess, but just to ask you, here we have a slightly unfamiliar example in the end of ADS-CFT, at least compared to normally, in that for part of the boundary you have dynamical JT gravity, and just from the rules of ADS-CFT, what is the dual supposed to be? If I had a boundary CFT2, the rules would be ADS3. And now that I have boundary with partly JT gravity, the dual is ADS3, but
With JT gravity on one of its boundaries.
and that's it. I mean,
JT gravity here is part of both descriptions.
Essentially the conformal factor
suppose
is
I'm allowed to do
ignored
that
in this.
Or you're allowed to try, and then if you run into problems, then you say, oops, I was not allowed to do that.
But it feels good, right, Sandeep? The whole thing feels good. I mean, look at picture 1, then it grows it out, then it matches picture 2 to picture 3 also. That feels good.
In picture 1, if I applied the naive description, Takanagi's description, so that's the boundary conformal field theory L and the boundary conformal field theory, or 1 and 2.
Okay? Left and
Now,
right.
I think their description would have been that you just take half of the
ADS3. Yeah.
Poincare radius there and half of Poincare radius there.
Yes.
They wouldn't match up,
Yeah.
okay, like the way you were thinking.
Yeah. Yeah.
Now, I presume that if you have dynamical degrees of freedom there, like a
Yeah.
zero brane or
Yeah.
something,
Yeah. Yeah. It should be allowed to do whatever it wants. One thing it can do is match up.
Match up. So,
That's
but
right.
how do you know that it matches up? I mean, why is it not a disconnected there?
Well,
Two
that's
disconnected paths?
That's because we started with this picture. This picture tells you that they're matched up, right? Because this thing here is this plane here, is this strip.
Suppose I didn't know anything about
Yeah, if
except that figure 1.
Yeah, so
Equation 1 is all I know.
yeah, then I wouldn't a priori know.
But you know that you were working in a state in which these two are not unentangled with each other.
Exactly. So we know
That suggests that.
exactly.
It's like
It's the same thing if I give yeah, exactly. Please go on. It's just like the thermal field double. You have two CFTs, and in some states they're connected, in some states they're not. Yeah. Yeah. Let me see. Do I have any other comments to make?
ER equals ER, of course, because the entanglement leads to the bulk conductivity. That part is clear.
Yeah, as in some region in the bulk here becomes dual to the bath, and it was generated because I don't know about because, but it's it saved you from this ever growing entropy, right? The entropy keeps increasing, and then now you have an island. And so it's the same set of words that Lenny and Juan have been saying, that after you build up entanglement so much, the Hawking radiation becomes dual to the interior. And this is a precise manifestation of that. It had no business of being this simple.
That's what I was going to say. You probably have some comments, but I mean, how, if you try to directly compute the corrections in the radiation, which would make that curve which was going up and up come down, are probably horrendously complicated corrections in the density matrix, right?
Uh,
I was just going to say, picking up on what Ahmed said at the end, and he's probably going to amplify that. I mean, what's truly shocking is that such a childishly, if I may say,
Please, no.
no reflection on you, but Sorry, I didn't.
No, 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 no.
What I meant was such an amazingly simple calculation would give us. Sorry, I really didn't mean it. But it's an amazing, shockingly simple calculation. Gives us the entropy.
I would say that's an art, right? Finding a simple calculation that gives you something deep.
Yes.
Good.
But if we were to attempt a direct calculation in the just in the radiation itself, right? Because you did is without appealing to all of this, you say, okay, I'm just going to sit out at Scri plus and try to compute the entanglement in the radiation. Then you have the zeroth other thing you do in the semi-classical limit would show this thing growing.
Yeah.
And then presumably there are 1 over Gn corrections, which you left out.
I would say e to the minus 1 over gn.
E to
correct?
the, okay,
Yeah.
even better,
Yes.
yes. E to the minus 1 over Gn corrections, which one left out, which will in the end give this,
Yeah.
that's what,
Yeah.
but here without any of that,
I would say the following thing. So here's some vague set of words that, in some sense, so we did the calculation in 2D and we got the wrong answer. There we assumed a semi-classical approximation, like what Hawking did and what you guys did and what everyone else has been doing, and we got this wrong answer. In some sense, working in 3D, I want to say that by working in the semi-classical limit in 3 dimensions, this goes beyond the semi-classical limit in higher dimensions, on the boundary, sorry. And but to make this a bit more precise, it's not just okay, these might be the same thing, but let me say it anyways. It's not just a semi-classical approximation in 3D, but it's that coupled to the Ryuta-Yanagi formula. I think that formula is very deep, and it knows a lot of things about the theory, and it is sensitive somehow to these non-perturbative effects. So working with those 2 things goes beyond the semi-classical limit on the boundary. That's what I want to say. And that's going to be something I'm going to talk about. I guess that's going to be in the next lecture, right? Should wait for Abhijit, right? Yeah.
It's like small corrections of something. A state can change an order 1, but lead to very small correction in many measurables, right? So that for many measurables, you've got some e to the power minus g.
Yeah.
But the state in the Hilbert space itself is very different.
Yeah.
And somehow Ryuta-Yanagi computes that. Right? But we know in the gas, there are 2 very different states that will give you the same expectation value for most reasonable things. But
Exactly.
the state could be totally different.
Definitely.
And a totally different entanglement. But somehow Ryuta-Yanagi is clever enough to get, because it's an order 1 change, even though it's e to the power minus.
Yeah.
That's the surprising thing.
Yeah.
Because it wasn't an e to the power minus g of the state. It was e to the power minus g of some observables. Right? Minus 1. Yeah. No, not the state. The state is really just order 1 different from what Hawking said.
have to.
Yeah.
I'm just going to write this formula down again.
This Newton is 2-dimensional G.
Sorry?
2-dimensional G Newton.
No, this is a general statement.
Right. In this context, it will be 2-dimensional, not 3-dimensional.
That's right. I just want to make a comment about this formula. This formula is weird in that it has a von Neumann entropy on both sides. To compute the von Neumann entropy of B, here you have to include von Neumann entropy of B union I.
Sorry,
But
B is the path.
yeah, B is some subregion in the bath, and we have to look for islands in the gravitational region, right? This is what this justifies. I just want to make a comment about this formula, which is that it seems confusing that there's a von Neumann entropy on both sides. But one should take this as a prescription, where if you want to compute the exact entropy of the bath, there exists a calculation within the semi-classical approximation that captures that. So this von Neumann entropy should be thought of as that which is computed in the semi-classical approximation. Okay, I want to keep this. This is what I wanted to end with, because and then in the next lecture I will derive it. Well, give you comments on how to derive it.
And what's the general then prescription, which is, you know, if I just handed you, I could have just handed you the late time state of the bath with no reference to how that state came about, and then of course.
Ah, no.
No,
I'm not going to allow you to do that.
No, I know you're not, but I'm just posing it. And if you were strong enough and you could compute e to the minus g and fx in that state, etc., you could have done this calculation just on the path.
That's right.
Right? But the statement is, you know, if that state arises because of complicated interactions, including gravity ones, in the course of its preparation, then allow for the possibilities of islands in that path, which is now
Exactly.
not of relevance for the state directly. I mean, that is look in terms of space-time locality far away, and they can still contribute.
That's right. In fact, even just to make you as uncomfortable as possible, let's consider an evaporating black hole and whatever, an ADS or whatever, but it's a small black hole. You know, we often draw this diagram, right? So whatever, maybe it's ADS. We have all this radiation that comes out, and it's all the way here now. So I just have a bunch of radiation. So it's a black hole, a pure state below the Hawking-Page transition, so it evaporates away. It's a small black hole. If I want to compute the entropy of this radiation, then use that formula. This can be arbitrarily far in the future. You have to include an island here. That's what gives you the right answer.
Because this HRT thing allows you to.
Exactly. Yeah. And in this process, you're supposed to extremize over all islands that can be anywhere in the space-time. And to make you even a bit more uncomfortable.
Sorry, just to make sure I understand, we could. So let's conceptually take our radius to be very big in a
Yes.
sense. You can make a pretty big black hole, you know, if our radius is light years.
Sure.
Which is still small.
Yes.
But pretty big, and let it evaporate away. And you say that you do get the correct Bekenstein-Hawking-Worth, roughly, of entropy in the radiation in the end, and no more by including the ion.
You get zero.
You get zero. I mean,
Well, if you made it out of pure.
yeah.
Yeah, all right, okay, let's make it even. You're right, you're right.
Yeah.
But if you make, okay, pure, then that's what you would do.
Could I ask a related question?
Please.
The question is, okay, so far you've avoided talking about Hawking's derivation and all that. But I want to know how this ties up with what Hawking said would happen.
Yeah, so, can I rephrase that question as saying, where was Hawking's mistake?
And to what extent is he correct?
Yes, I would say his mistake was that he didn't know about the minimality condition in the RT formula.
That's great. So what I want to know is that it seems to me likely that if what Hawking said would continue to be correct locally.
Yeah, I agree.
That if you didn't look too far away, it would just be completely right. And it's as you said many times, Hawking's process is correct. It's just that what's happening here is a proxy for what's happening there. But if you just look locally, you didn't try to include here and there being the radiation, Hawking would be just exactly right.
Okay, exactly is a bit.
Exactly maybe it's too much. But
Okay.
it will be very close to right.
Yeah.
Here is near the event horizon, and there is far radiation.
Yeah.
So you take a box near the event horizon, and you ask, was Hawking right in that box? We don't go too far. And the evolution would be just exactly as he said. How could it be?
Yeah.
No, the point
For the
is-
state itself.
No, I think that's true. And
No, you're looking at a small subsystem. You're looking at a small subsystem of a larger system, and so you don't care about the
But
correlations.
now, I mean, now the question really has he write up to order e to the minus gn?
No. I would say he was not.
Yeah, he's not, right? But
That's
you have to keep track of the corrections up to order e to the minus gn for this final.
But I thought at the fundamental level what's happening here is that what's happening here is a proxy for what's happening there. So Hawking already saw that the state was changing at order 1 because he saw that the a tilde mode was some order 1 thing. And then there's a dictionary for what's happening here to what's happening there. That is the complicated thing. But that it's affecting the late time radiation at order 1 was there in his calculation. If you just knew that there was this identification.
No, I don't know what you mean. I mean, okay, first let's do it at scribe plus. There are e to the small corrections which add up. Suppose that's the underlying state.
Yeah.
How do those small corrections arise? They will arise also if you try to do it Hawking's way, because you know the dynamics near the horizon will also change as a response to quanta going out.
No. The state across the horizon is, as Shiraz was saying, the state across the horizon is still the usual Hawking state, but now you have an identification of a tilde with the stuff outside.
Well, I mean,
The thing that builds up is whether the inside is dual to the outside or not.
That's true, but I'm saying eventually you might hope to do a calculation, you know, in the bulk itself.
But if you're going to calculate the state, you have to know the rules for what builds up the Hilbert space. And if the Hilbert space is just, if you try to work semi-classically, the semi-classical picture has 3 different Hilbert spaces. And that starting point is just totally wrong according to what these guys are saying. So you'll never be able to get it. You'll have to have a new framework to do it. It seems to me. I mean, if you're thinking of correlation functions, you might be able to get away. But here you're asking a question about what is the state in the Hilbert space? So you have to know approximately what was the Hilbert space before you start making some approximate.
What's the precise question, Shiraz?
I want to know, let's say, if
How would you do the calculation in the bulk to get the correct answer?
I don't,
This is your question.
This is my
Hawking
question.
did a 0th order question. The calculation, how would one improve?
let me go to the board.
Yeah.
Okay.
I'm going to fix Shiraz's seat.
Okay, so this is the horizon, this is the box, so this is the radiation. Okay, Hawking did a calculation to compute what the state was here and here. And I want to conjecture that this was more or less correct.
Yeah. I agree.
That's not the art of the issue. That this was.
No, let's ask the question. Hawking computed the state of radiation at scribe plus.
Right, he got
Okay.
that completely wrong.
He got
Yes,
it wrong.
yes.
What would you have? I thought that's what you were asking, no?
Yes, but I'm saying that what he got wrong was not understanding that this part was not in a separate Hilbert space from this part.
Yeah.
So he did a computation thinking that was H1, H2, and H3, and he wrote down a state in the direct product Hilbert spaces of H1, H2, and H3, and that entire formalism is wrong, according to these guys. According to Pablo Dimas, according to compliment them. What he should have realized was that the whole thing was in something like H2 cross something, which is either H1 or H3 or some combination of it. Okay?
But let me also emphasize that at early times, it is a good approximation.
It is a good one. Right? Yes. Now, if you were to do the calculation correctly, there would be 2 parts. Calculate what's happening here and figure out the dictionary.
Yeah.
These 2 steps would be needed to calculate what's happening there. The step we don't know how to do is to figure out the dictionary. Okay? And that is the part that requires, it seems to be a new format. But the radiation is changing at order 1.
See, I think there's an even more, I mean, since the corrections required are so subtle, even that box is not well defined. I mean, could you have a semi-classical notion in which you would be able to compute the e to the minus gn corrections?
Possibly in the next thing I'm going to talk about.
Okay, but it's not clear to me. It's not clear to me that they are not totally different saddle points or something which are required when you phrase the question
Yeah.
correctly.
But even within the box.
Even within the box. I mean, the notion of a box, of a semi-classical geometry with which you foliate and then you do the calculation, there are interpolating configurations. Let's phrase it like this. You're trying to compute the S some initial pure state at scry minus and scry plus. Hawking had one interpolating semi-classical configuration. There could be others. Would they be all small corrections or whatever? I mean, they could be just something totally different, right, in the bulk. So then you would be drawing these boxes
Yeah.
not in a given
The
geometry.
main thing is these Hilbert spaces not being the same. You may not need more than that.
It's not clear to me. It's not clear to me because even the notion of the box.
I agree, maybe slightly imprecise, but it seems to me that the suggestion is that the main change is this.
Yeah, that follows from that formula.
Yeah.
No, but we haven't done the calculation in an honest way yet, right? We don't know what the corrections are. They're very, very sensitive.
Yeah, so
Do we know that there is one bulk semi-classical geometry which contributes more or less? I mean, to get the final answer?
but for the
No.
entanglement entropy, they know how to do it, right?
No, but the entanglement, it's an amazing formula which gives the correct answer in a semi-classical way to this very delicate object.
But okay, how about this? So the entanglement entropy is the computation where you compute trace row to the n, and then you take the n goes to one limit in a fancy way and so on, and take the derivative. Okay, but you could not take that limit, and you could just compute literally just trace row to the n for a different n, and that gives you more and more information about the state of the radiation. And it's clear that in that calculation you care about these other saddles.
Correct.
And so already, I mean that's an example.
So I'm just saying, suppose you have other saddles which are contributing.
Yeah,
Each saddle comes with its own notion of geometry.
yeah,
You know, you would have to, there wouldn't be a way to relate the box in one geometry
Yeah,
to
I agree.
the other. That's all I'm trying to
Could
say.
it be that even if you do only one saddle point calculation in the box, so your answer is not precise enough, but for the question of entanglement, if you can figure out this mapping, how to take the phrase, because you want to know understand the relation between Hilbert space of radiation and the inside. So you know the mapping very precisely, then probably you can, from a wrong calculation, which is not precise enough, but still you can figure it out probably. Because this mapping is very non-trivial.
And maybe all the complications are in the map. Maybe the rules for the map are very complicated.
Oh, definitely. Yes, yes.
The rules for the map are complicated, but
You will not get everything right, but maybe you can still get the entanglement entropy right with the map and the wrong state.
but how do you propose the map across
We need a
geometry?
rule for manners.
But across geometry? I mean, I think what I'm trying to ask is it's not entirely clear to me that a semi-classical calculation with small corrections is enough. Because they're very subtle corrections that we have to compute. So maybe your replica trick calculation, I hope you'll describe it.
Yeah, I will.
That will give I mean, that was the spirit of Juan's old paper where he had the version of the information puzzle, right, which you all have emphasized to me, that there was another saddle point.
Yeah.
I mean, there seems to be, from what you have said to us already with the replica trick, that the intrinsic 2D description is here also kind of analogous to that. No? That's all I'm saying. Then it becomes a little harder to say, okay, now there's a box where everything is, at least for me. I understand that the interior is being encoded. I understand that.
The Hawking, if we could somehow stop the evaporation by putting some boundary conditions, let the Hawking radiation go infinitely far away and restart it. And what I want to say is that
Okay, we can do that here.
we could do that, right? So what I want to say is that any reasonable semi-classical notion of communication from here to there could just go to infinity. Could be completely cut off, and it would still be happening. So that would just be a dictionary issue. It seems to me.
So the Hawking evaporation goes out for some time and then cut off meaning you reflect it back.
Put a wall around the black hole for a while, stop it from evaporating. Let the Hawking radiation go out arbitrarily far for us after Einstein. Okay. Now let it continue. I'm not sure exactly how to do it.
Continuing, then after that it will bounce back.
After that, now we'll start Hawking radiating.
You start with transparent boundary conditions, then you go to reflecting, and then you go back to transparent.
Okay, in between it's reflecting and then
Then,
starts
yeah.
again. Okay.
So that we just make the causal connection between this arbitrarily bad. Yet, what's going to happen, it seems to me in their picture, is that every time a new Hawking ray mode is emitted, it will
sure exactly when you want to stop it, but let's say,
No, I think it means the radiation.
I meant the radiation. But I mean, just to say that, okay, suppose there's enough radiation outside,
Yeah.
so that,
Three-fourths has bigger.
yeah, so we are, so to say, after the page time, right? Now one more quantum comes out. Now it's highly entangled with the radiation.
Yes.
And even with the early time radiation.
So the new quantum that comes out has to unentangle the radiation to a bit. Every one that does it removes some of the entanglement of the radiation, even though it's infinitely far away.
Yeah.
It's a dictionary thing, because it's Hawking explained to us that it's this A tilde, but A tilde is part of that. That's just, in some sense, it's that. How it seems to me that if this is correct, the question is what is the right formalism, and how does that formalism preserve causality?
But see, it's because of the causality aspect that I'm coming back to the fact that this notion of semi-classical geometry may not be enough for this question.
This idea.
See, well, how do you semi-classically understand this huge non-locality?
Yeah.
That ER bridge of yours, even to go back to what I thought was a typically Lenny, absolutely crazy idea that each Hawking pair is a ER bridge. And that's not a semi-classical geometry notion.
Well, but it is in this case.
In
bridge-
higher D,
The
in
bridge,
higher D.
the bridge is in higher dimensions. Yeah.
Yeah, in your miraculous higher D for the real Takanagi, but I'm saying pair by pair.
Well, I mean, something. Okay, this is not that precise, but something you can do is you can split the Hawking radiation into small patches. So take some. Okay, I don't know how you're going to localize them, but let's say you can. And you have some radiation here, and so on, and here, let's say, and we know that the interior ultimately is going to be dual to this radiation. The RT surface is going to look like this. Am I drawing this right? So there was radiation there, there was radiation there, there was radiation there. So this is where the radiation is. The reason why I'm drawing it this way.
And what happened in between? You stopped the, you had,
I'm-
reflecting transmission.
No, I'm just lumping the radiation into small regions. The reason why I'm drawing it like this is I'm trying to get this octopus picture that Lenny and Juan had, right? Where every Hawking quantum had like a wormhole connecting to the black hole. That's like this, right? So I had some radiation here, here. So you have all these legs. This is not precise. This is just.
Yes, I get your point. I see. Those legs are connected.
Exactly.
So my comment is that we have a bunch of tea outside.
Oh, is that right? Is that right?
Yes.
Which has become iced tea by now.
Anyway, let's thank Amal for a great.